Okay, so this will be a continuation of this proof of regularity of holomorphic functions. In particular, it is infinitely differentiable if you're holomorphic, and um, also it has local power expansion. Okay, so it is analytic in that sense. So previously we've showed Goursat's theorem and fundamental theorem of calculus. And just to review, Goursat's states that if you have a holomorphic function on an open set that contains a triangle and the inside of that triangle, then the closed loop integral, the contour integral along the triangle of this holomorphic function will be 0. Okay? And the idea is that because it contains this interior portion of this triangle, we will, quadrisect this triangle into smaller pieces and show that it is bounded by, some factor times the integral along one of the small triangles. Now, by Bolzano-Weierstrass, this nested triangle contains a common point, and our function is holomorphic about that common point, which means f prime exists at that point. Then we can estimate this function to write it as some f of z naught plus this derivative value times z naught plus some continuous function, where this continuous function rz goes to 0 as z goes to z naught. And this first portion, it's a polynomial of degree 1, and that has an antiderivative, so by fundamental theorem of calculus, this vanishes under this closed loop integral. Then it remains to estimate this integral right here. And we saw that this factor z minus z naught is no bigger than the perimeter of that small triangle, and this value of rz, because it's continuous, that goes to 0, it is bounded. This is some constant. So the math shows that this integral that we want to integrate along this triangle is less than some quantity that goes to 0 as n goes to infinity, hence showing this is 0. So Goursat's, again, for triangle says if you holomorphic on an open set, then that contains a triangle and its interior, then closed loop integral along the triangle will be 0. Okay. Now, next, what we will establish is the existence of a primitive on an open disk. So how does this work? So maybe we can even replace the term open disk to star-shaped domain, but we'll do open disk for now. The idea is we need to be able to contain line segments whenever you choose 2 points in this set. So technically we can relax this condition to star-shaped, but an open disk will do. Okay. So what's going on over here? So say you have some open disk D. And without loss, we can just translate the function so that the center is at 0. So without loss, let's just pretend the center is at 0 for this disk. Say the center of D is 0. Okay. Now, what is it that we want? Well, we know that it is holomorphic, and what we want to do is to construct a candidate for a primitive. We want to construct a function that could be its derivative, right? Or whose derivative is little f. So what we will do is this. We'll define this big F function, f of z, for each z in the set D, to be, well, how about just the line segment integral, 0 to z. So this is the notation. Maybe I should say, this curve 0 to z like that. Okay, so this is just the line segment. This point is z. just integrate from 0 to z along this curve of f of, well, I guess I better use another value. Let's say f of w dw, like that. Okay, so I'm going to define this function. So for each little z in D, we can calculate this, right? Because f is holomorphic. Well, we didn't show this, but it is in particular continuous. So after you parameterize along this path, this gives you some number. So this is a function. This defines a function. And what we claim is that, well, this big F that we defined is indeed the antiderivative of little f. Well, how do we show that? So we will claim f prime is equal to little f on this disk. Now, here's where the geometry of this disk actually matters, because it's a circle, so it will contain every line segment. Whenever you pick 2 points, it will contain the line segment joining those 2 points. So we care about this being an open disk. Okay, but how do we do this, right? Well, we want to calculate the derivative of this. To calculate the derivative, well, we need to consider the difference quotient. So, okay, so consider, say, well, how about f of z, let's say we're differentiating at z naught plus h minus f of z naught, like that. For z naught in D and h small enough, right, such that z naught plus h is also in D. So we're well within this open disk. Okay, so this is a z naught. Say this point is z naught plus h. Okay, so we have this minus this, so we ought to get something like this, right? Okay, let's see. This minus this, so it's this. Yep. So notice, okay, if you were to join these 3 pieces, we'll get a triangle, right? So the triangle, let's call this T for now, T, which goes from, say, 0 to z naught plus h to z naught back to 0. Okay, so this particular triangle, if you were to integrate t of f of z dz, this is equal to 0, right? Because this is well within our open disk D that this is holomorphic on, and this triangle, because these are line segments, this is well within this T. So notice we have this by Gauss-Sachs. Okay, so here's where we use Gauss-Sachs. Now, notice this triangle, it really is just these 3 pieces, right? From 0 to, so what did I say, z. So I did this in a counterclockwise way, so yeah, sure, doesn't matter. Like that. Plus, this is z naught plus h to z naught plus z naught to 0 of f of, I guess maybe we should write, yeah, f of z is fine. F of z dz, it is 0 because this is just t, and this part right here is precisely f of z naught plus h. This part right here is precisely negative f of z naught. So we see that, this is just subtle usage of Gauss-Sachs, but it's obvious now that we have f of z naught plus h minus f of z naught is precisely the integral from z naught to z naught plus h of f of z dz. Okay. So what we need to do is to calculate this divided by h and see what happens. Okay. So let's actually just write that in there. So f of z naught plus h minus f of z naught divided by h is equal to 1 over h of this line integral. Okay. Now, what do we do here? Well, why not just let's maybe estimate this. Yeah. Okay, well, since f is continuous, well, it's holomorphic, so it's continuous. Right. By the way, where do we use holomorphicity? Gorsatz, right? And T, I, T, both in D, right? This is where we use this holomorphic part. But here we just need to use that f is in fact continuous at z naught. So f of z is equal to f of z naught plus some function r of z, where this is just a constant, where this function r of z goes to 0 as z goes to z naught, right? Okay. So, all right, 1 over h of all of this dz, it's 1 over h z naught to z naught plus h of f of z naught, it's constant, plus r of z dz. Okay, so here a simple continuity tells us the limit. This is just basic analysis, right? Now, this is a constant, so we have 1 over h integral of f of z naught of z naught to z naught plus h of 1 dz. Well, this is just z, so this is going to give you h, okay? Plus 1 over h z naught to z naught plus h r z dz. Okay. So this whole term turns into f of z naught because this integral is just h. Okay. And what about this, right? So let's analyze this. So we'll analyze it in the limit. So since let's bound this out, the magnitude of 1 over h of integral from z naught to z naught plus h of rz dz no bigger than 1 over h of the length of this thing, the length of this integral, times the maximum of rz on this path. Well, as h gets smaller and smaller and smaller, well, first of all, this is just equal to the max of magnitude rz on this path. And rz goes to 0 as z approaches as we're near z naught, right? So when h goes to 0, this the value of r goes to 0. So we see that this goes to 0 as h goes to 0. So hence, we see that the limit of f of z naught plus h minus f of z naught divided by h as h goes to 0 that we calculated, it is just equal to f of z naught right here. Right? This other part goes to 0. As h goes to 0. Okay. What does it show? That shows that indeed f, big F prime, is equal to little f for every z naught on D, right? So this is true. Hence, f prime is equal to little f on the open disk D. Okay. So subtly, where do we use the fact that there's an open disk again? Because of the geometry, right? Because if this is not an open disk, then we cannot guarantee that this triangle, when we pick these 3 points in here, this triangle will be inside this open disk. So we couldn't apply Gorsov's in that case. So this, in a very subtle way, just really silly way, that it depends on the shape of this disk. So we can, if there's a shape that says, well, for any 2 points, the line segment is in it, then something like a convex set would do, right? So you can replace it with any convex set. I think you can also just modify this to star-shaped as well. But what if it's outside? Yeah, that's possible. So maybe at best we can replace this with convex. But this is sufficient. This is pretty good. Okay, we have this antiderivative. Now, what does that mean? What's a consequence of this, right? Having this, having a primitive on this open disk. Well, remember, the immediate consequence of having a primitive is that any closed curve integral inside that set to which it has a primitive on, then this closed curve integral will be 0. So immediate consequence is this. If f is holomorphic on open disk, then for any curve, any closed curve inside the open along gamma, this contour integral over gamma, f of z dz is equal to 0. That's the immediate consequence. So it doesn't matter what gamma looks like that, So again, because it has an antiderivative. So this is very simple. This is basically a kind of Cauchy theorem result. But maybe we can even upgrade this, right? Because maybe we're not just holomorphic on this, but we're holomorphic on some big open set. So this is how we typically would state Cauchy theorem. What number are we at? 3. So maybe we call this we can call this Cauchy theorem, I guess. Okay. But what we can also say, rephrase this is in this following way. Okay. So this is also Cauchy theorem. Basically, these are just results saying that things integrate to 0. Okay. So this one, so maybe this is Cauchy theorem on the open disk, but this one is Cauchy theorem of a circle, integrating along a circle. So suppose f is holomorphic on open set U that contains a closed disk. D bar, so it contains not just the open disk, but it's also its boundary. Then the integral along the boundary of that disk of f of z dz is equal to 0. Okay. So both of these, you can think of them as Cauchy theorem, doesn't matter, as long as you know using it correctly. Now, why is this true? Well, let's say this is your open set, U, right? It looks kind of weird. And say it contains this closed disk. Okay, so it contains this boundary as well. And we're integrating along this boundary like this. Well, firstly, because it contains a closed disk, and this closed disk is compact, one can prove that there is in fact another open disk that sort of that is around this closed disk that is still inside U. So there is an open disk neighborhood of this closed disk in U. So proof, okay. Since D bar is compact, okay, in U, which is a subset of the complex plane, specifically the complex plane. So we use Heimberg to prove this. This is a separate proof, but there exists some other open disk. Let's call this D prime, such that D prime contains this D bar, and it's also in U. Okay, so this is D prime. Okay, so this closed disk is inside some other open disk inside U. This is a result from, just metric topology. So separate fact that we can prove this later. So let's think of this as a lemma. Let's prove this later. Proof of it later. Okay. But let's say you believe this. Then by the previous Cauchy theorem, because this D bar is inside this D prime is a open disk, so F is holomorphic on D prime. So by it has a primitive there, so of course any close loop, it will integrate to 0, including the boundary of D. So since F is holomorphic, this is just crossing the I, dotting the I, crossing the T here. Since F is holomorphic on open disk D prime containing the closed curve boundary of D, then we have precisely what we want, the integral along the boundary of D, f of z dz is equal to 0. Okay, so pretty straightforward. All right, and we will use this quite often, integrating along a circle, things of that nature. Okay, maybe we want to just take a break and prove this metric topology fact about this this thing right here. Maybe we want to prove this. So why is that true? So maybe I use a different color, gray. So here we use this lemma. Okay, this lemma being, if U is an, I'll just say it's an open set in R2. Okay, you can upgrade this to Rn if you like, but let's just do an R2 for now. In R, okay, let's just do Rn. Let's do R2 for now. It's an open set in R2. Okay, easily, replaced to higher dimensions. So here, this is with respect to the usual topology. Right? We're in complex plane. We're using the usual topology, the metric topology of these Euclidean spaces, and that's important. Okay. If you use an open set in R2 containing some closed disk D bar, then there exists an open disk D prime such that D bar is inside D prime is inside U. Okay, so precisely what happens there. Okay, how do we prove this? Well, several things. Because a closed disk, let's just say the closed disk has center some C naught, right? And because it's a closed disk, it's closed and bounded, so we're in R2. So by Heim-Borel, this is compact. Okay. So notice D bar is compact. Okay. Now what's nice about compact sets is that if you have a sequence of points in a compact set, then there is a subsequence that converges. Right? This is Bolzano-Weierstrass in many ways. Right? Okay, so we will keep that in mind. So let's prove this fact. We want to prove the existence of such open disk D prime that sandwiches between them. Suppose there is none, right? So suppose, to the contrary, no such D prime exists. All right. So let's say the center is Z naught for D bar. Okay, for D. So suppose there's no such thing. Okay. So consider the sequence of open sets. So consider I'll write it as Dn to be so let's say D bar is equal to the set of all complex numbers. Well, we're in R2, but you can imagine what I mean by that. Z minus Z naught is less than equal to, say, it has some radius, let's say R. Okay, R. So consider these Dn's is a bunch of open sets such that Z minus Z naught is less than R plus 1 over n, right? So basically just slightly larger, by 1 over n, and in the radius of the original D bar. Okay, so these are open sets. Since we're assuming to the contrary that no such open disk exists that can contain this, that can sandwich between D bar and U, this means that D bar is not in Dn. Okay. For each n. Right? Because if one exists, then we're done, right? So we're assuming that no such open disk exists. Okay. What does that mean? Well, that means there is a point in Dn that is outside of D bar. So let's call the Zn, let's say, in Dn that is not in D bar. All right, so let's draw a picture. Say this is our D bar, and well, I actually I should say that is also in U, right? Okay, so this makes no sense, right? This makes no sense. So we want to have, hold on, of course D bar is always in Dn, but it's not in U. Okay, so it's the not in U part that is hard. Okay, so notice. Okay, yeah. What am I doing here? Okay, it's the U part. Okay. So notice D bar is in Dn. That is for sure. This is by construction, right? By construction. So what will break is that Dn is not in U. So it must be that for each n, Dn is not in U. There we go. There we go. So what does that mean? Okay, so this is D bar. This is dn. So u may look something like this. This is u, right? So dn I just cannot fit inside u, basically. Okay. Well, what does that mean? That you cannot fit inside u? That means there is a point in dn that is outside of u, right? There is a point in dn, and because it always protrudes, if it's always inside, then we're done, right? So this means there exists some zn in dn such that zn is not in u. Okay, you can always find this point. Okay. So let's see. Now, because it is not in u, and d bar is in u, the zn is also not in d bar as well. Okay. So say, for example, in this picture, maybe it is this point right here, right? It's outside. Oops. Okay, it's this point. Let me draw u better. So this is u. U is this weird shape. The stuff inside is a d bar, and here we have a point zn. Okay. And well, what can we do? Well, let's say this is z naught. Well, let's see. We can kind of relate to this thing. So we can say that, okay, maybe zn is equal to, because we're in Euclidean space, so I can say that it is something plus something. I can say that it is some, maybe this point right here, if we draw a line like that. Okay, let's draw a line. It is some something on the boundary of D, some yn, plus some little segment to zn, to become zn, right? So what we can do is this. By joining the center z naught to zn, we can find some yn in the boundary of D such that what? Yn plus some hn is equal to zn. Okay, so this hn is this distance. Okay. Where this hn, one can surmise that, well, yn has magnitude, yn minus z naught, right, has magnitude r, right, because the distance to z naught is r. It's on the boundary. And zn is within dn, so hn has a magnitude that is less than 1 over n, right? So we have this. Okay, so this is what we have so far. Now, yn being in the boundary of D, which is part of D bar, by Bolzano-Weierstrass, there is a convergent subsequence. So since yn is a sequence of points are in Dn, are in D bar, and D bar compact, by Bolzano-Weierstrass, there exists a convergent subsequence y and k that converges to some y star that is in certainly In fact, the D it's in D bar. In fact, it's going to be on the boundary because the boundary is compact as well. Okay, so we have this converging subsequence. Okay, so what? Right, so what? Well, then we can correspondingly look at Zn. So note the corresponding Znk, yeah, minus Ynk, this is equal to Hnk, this goes to 0. So what can we conclude? Well, we conclude that the Znk also converge to Y star. Right? Triangle inequality. Right, so this is less than blah, 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 blah. Okay. Okay. Right. Right. Well, if what we can do is also this, right? So this minus Y star is less than equal to Znk minus Ynk plus Ynk minus Y star, and this is less than equal to, this is magnitude Hnk, which goes to 0, and plus this thing, Ynk minus Y star, this goes to 0, this goes to 0, right? Okay, so it goes to 0. Pretty straightforward. Basic analysis. Well, what does that mean? Well, that means there is a point Znk that is arbitrarily close to Y star, but Y star is in U. So Znk is gonna be eventually be in U, right? So since Y star is a point in U, right? Because Y star is part of D bar, which is in U. And Znk approaches this Y star, eventually Znk will be in U for all large enough index K, right? That's what it means to converge to interior point, right? Pick an open ball around the Y star, some epsilon radius. Then because Znk converges to Y star, then for this particular radius, there exists some big K such that blah, 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 right? So this is true. But what does that mean? That means there is a Z point is in U, but these Z's are constructed to be not in U, and that's a contradiction. This contradicts the construction of all Zn that is not in U. So, what does that mean? That means there is some, in fact, there is an open disk of this form, Dn. There exists some n such that D bar is in Dn, is in, well, actually, it just shows that there's some open sets, some open disk. Okay. That is in U. Okay. Right. We could have just contradict the fact that suppose there is no such disk with the same center, but the radius is r plus 1 over n that contains D bar, but it's also in U, right? So if not, then none of this is true, but that gives us a contradiction. So this is possible. We can always fit a sort of a halo open disk around any closed disk that is inside some open set. Okay. So what this gives us? Cauchy theorem. Okay. Okay. So this is nice. Now with Cauchy theorem, that this established, we can prove that well, if you try to do some circular integration, close in an open disk that contains its interior and its boundary, and it's holomorphic on this open set, then this closed loop integral will be 0. Maybe to emphasize, we will draw a little bit of circle here, like that. This is always 0. Okay. Now with this is now the penultimate step to proving everything works, proving the regularity, because the next thing that we'll establish is Cauchy's theorem, Cauchy's formula. Okay, so next we will show, this is number 5. Okay, so using this Cauchy theorem, we will establish Cauchy's formula. Now this is done pedagogically in this way because all of these these theorems that we use are all going to be useful in solving some problems. So I'm sure there are direct ways to prove the regularity of holomorphic functions, but this is the pedagogical approach, which is kind of nice, builds up to that. And in the meantime, using tools that will also be useful. Okay. So Cauchy formula basically is this. Okay. Let F be holomorphic on some open set. Holomorphic on U that contains some closed disk, center as Z0. Bar center at Z0. Then we can in fact extract the value of F by doing some closed loop integral along the boundary of D. And further, we can get all its derivatives. So that's kind of neat. So this will be in 2 parts. We'll do it next time. But then what we can conclude is this. Okay, so first, draw a picture. We should always draw a picture. Some open set U contains as close as D bar, S enter Z0. Okay. What we're going to do is we're going to integrate along this boundary, and that will somehow tell us the value of F at Z0. And so here it is. Then the value F of Z0 is precisely equal to 1 over 2 pi I of the closed loop integral along this boundary of D of F of Z divided by Z minus Z0 dz. Okay, so this is part 1. And in fact, and also for using this is part 1 of the formulas for each integer m. Okay, let's say positive integer. The mth derivative, the m being 0 being the 0th derivative, meaning just the evaluation of f. But the mth derivative as Z0 is equal to m factorial divided by 2 pi I times the closed loop integral along this. This is all counterclockwise integration, by the way. F of z divided by z minus Z0 to the m plus 1 power. So all is greater than 0 dz. So this is the key to the kingdom, really, right? This basically says that the mth derivative always exists, right? So long as you're able to contain this closed disk. Now, this condition is very easily satisfied because if you're holomorphic on some open set, let's just make U open. No big deal. Then each point is an interior point, so it's contained inside some open ball, and that open ball has a smaller open ball whose closure is in, O in U. So this is very general, right? It's very easy to find a closed disk in the open set, right? At least in the plane. So here we have that if you're in fact holomorphic, then the derivative as Z0 for any order always exists because we have a formula to calculate this. This mth derivative formula is done by induction, and the base case is precisely the first formula right here. That will be the base case. So next time we'll show that the base case is true, which itself is useful, and then we'll use that to prove by induction all these formulas. These formulas are very useful. They can prove many theorems on their own. So important that we'll put a star. Maybe we put 3 stars. Okay. So, okay, that's it.